Start recording already? All right, so welcome back, everyone. So let's go back to the code. So I'll take the loss for granted now. I know it's a little bit complicated, but you can go through it yourself as well. I just wanted to give a brief explanation of what it does. Then I think it's just the main part that is missing, and we're done with this notebook, which is the longest one. Don't worry, the others are very short. So here, we have the transform thing that I mentioned earlier. We can transform images to do whatever we want, but in this case, we just want to resize it to this dimension, which is the only input size of that the model accepts. Okay. If you have smaller images, you have to upscale them. If you have bigger images, you have to downscale them. If you have images that are like very wide but not very tall, so rectangular, you have to make them square. There's no other way. This is how your works, and this is actually how most models work. You have to rescale everything to a specific size. Then you can rescale it back in the end. So it's not that it doesn't work if you have a different size. It's just that it is limited in what it can represent. And then it makes a PyTorch tensor out of it, but that's it. So in the main, we take our model, we place it on our device. Again, CPU, CUDA, MPS, whatever you want. We use Adam Optimizer in this case. And we use this scheduler, which simply reduces the learning rate whenever the loss is kind of like plateauing. But we will run it for a few epochs, so this will not even do anything. We can load the model if you want from a file. We will save the model in the end if we want to load it afterwards. We can print a summary of the model to see what it does. And then we have our data sets. So this is the training data set with the transformations and the training directory, test data set. The data loader, we use 16 as batch size instead of 64 because of memory constraints, but you can use more if you want, if you have more RAM or video RAM. We shuffle because that's usually a good thing to do during training, but we do not shuffle in this one because this I will use just for evaluation. Yeah, and finally the test loader. I mean, nothing weird here. Should be just the usual stuff. Okay, then what we do is that we have our bunch of epochs. We train. So this train function only trains for one epoch and stops there. And then we call this function get bounding boxes with our training data, the model, and the threshold we want. And it will give us some predict boxes by the network and also the ground truth boxes so that we can compare. And then we can compute the mean average precision and print it. And then we can do, we can do the same thing with the test set. We're not supposed to do it usually. I just want to see how it changes over time. Like if it gets better epoch by epoch or at some point it stops. It's more of a validation set than a test set. Yeah, and then we save our checkpoint at every epoch so that we don't lose anything if something crashes. Yeah.
It's better to also stay in the static position.
Sorry?
The scheduler, you should also save it.
Yeah. Yeah, it's true. The thing is, this is really not used. But yeah, you can say that. So. Okay, then finally some evaluation. I will run the algorithm again, get the bounding boxes from this, and then I visualize them using the function I implemented. You can also visualize the target boxes if you want, but for now I'll just visualize the predicted boxes. But then I had the ground truth on another folder, and I export them here. I do the same for the training and the testing part. So that's it. Then there's this function if you want to predict only from a specific image or something, so you can call it, but we will not use it now. So let's run something and see what happens. Anything. What did you ask me? Yeah. Oh, thanks. It's not. Didn't get it for some reason. Oh, it's working now. Okay. All right. Architecture. Okay, and now here I print actually the summary of the model. So you see all the printout of the architecture. It's bigger than this. So you can see it here. It's again 24 layers. It's all of these. The only difference with the YOLO v1, like the full YOLO v1, as I said earlier, is the number of parameters in the fully connected layers, which are here, these, so 24 million parameters. Otherwise, I think it's going to be like, I don't know, maybe 100 million more or stuff like that, if we use the full size. Okay, let's training function, our loss, and the main. Actually, let me select the number of epochs. So 10 epochs is right now. Learning rate, we can keep it like that. So I'll show you on CPU just to see the speed first for one epoch. And the rest is fine. Okay. So here we have the printout for the training. So this 1 out of 15 is the number of batches in the training. And this is 1 epoch out of 1. And you can see it's taking around 7 seconds per batch, and the batch is 16 images. But this is training, this is not inference, so it's slower. All right, I can actually stop this and run it on MPS so that it's a little faster. Let's run it for 10 epochs and export the results. Oops. MPS is the neural engine of the Apple Silicon chips. As you can see, it now takes around 1 second per iteration, so it's way faster. You can train very nicely. So I mean, you know Apple Silicon? Who asked the question? Do you know Apple Silicon, like the new Apple processors? They came out a few years ago. They all have like, of course, an integrated GPU and some neural engine, which is basically just convolution operators. Matrix operators do stuff like this. So it makes this kind of things much faster, and it's a fairly good speed up, to be honest. I don't use MPS much. I usually like use a cluster with a big GPU and whatnot. It's quite cool. I mean, YOLO is not a huge model, but it's also not so small. It's like 90 million parameters, and it's training fairly fast. And we will see also, I'll show you right now the inference of the big YOLO V8 model, and it's going to be almost real time, even on a laptop. So let's just wait a few seconds for it to finish. This is what the training set looks like with the ground truth annotations. So you see that, I mean, in the ground truth, the confidence of the ground truth is always 1, but this is not the confidence we use to train the model. We use the IOU to train the model. And this is the class, Apple. See, like this, when there's more, all of them are annotated like this. Same. So, I mean, there's the model, like training for 10 epochs, it would not be very good with bananas. I don't know why. With apples, it's all right, but with bananas, yeah.
An image that really fine. Those are the only complete.
No.
That's a really
Yeah.
nice task.
You know, that's also the problem a lot of times with data sets. Maybe the network is doing the right thing for what it learns from the data set.
This is totally unclear what the task.
I agree with you. I totally agree with you. This is not a particularly great data set, I would say. It's just for showing. Even this, like, it doesn't select this one. I would say it's an orange.
You want to label those images. Is it not more usual to label every instance?
Yeah, I would say so. Sure.
And partial instances, how do you cope with that?
The boxes, the boxes are allowed to go out of the image.
Yeah.
And even if they're not right now with the current architecture, I have to check. I think they're allowed. If they're not, you can change something in the way the problem is formulated to allow the boxes to go out of the image. It's fine. That's not a big deal. Yeah, because the boxes, as I said, are expressed as a ratio between the width and the width of the cell, but there's no constraint on how large the ratio could be. So I think they can go out of the image. Okay, final iteration. So as you can see, there's a training mean average precision that is going up 11%, 18%, 24%. And now I should go a little bit higher, hopefully. 31%. It'll keep going higher the more I train it, of course. Also, the test one is getting a little bit higher, 6%, 7%, 11%. It's not a great data set, so do not expect crazy numbers. But even like such a low number, like 11 is low, I can show you the test set. It's not going to be great, but it has already learned something. It's not unusual. So this is an apple with 62 confidence. Apple, 67 confidence. Nothing, didn't find anything here. Apple, 53 confidence. Of course, some images are easier than others. Like clearly, this is a more difficult image than the other ones. This also couldn't learn much. Same. Apple and orange, clearly. But yeah, it's a very small training, but it has already learned something. So banana. Oh, something is happening, so that's nice to see as well. This is clearly an orange, according to the model. This is a banana, very clearly. This is an apple, finally. Try apple. So something is working, something isn't. But again, that's to be expected with such a short training. You can try to like use the same notebook with a bigger data set and a longer training and see what happens. Yeah, some bananas. I mean, it's doing something also on the test set. It's getting there, definitely. It just takes some time to train. All right. Any questions on YOLO V1? And I'll quickly show what happens with YOLO V8. So for YOLO V8, actually, let me terminate the kernel because otherwise I run out of memory. Okay, YOLO V8. So I actually use the pre-trained YOLO V8, not training a new one. So you can import them simply from the Ultralytics package. You can import basically any YOLO version from this, and it's very easy to use. So you get it like this. You load it, YOLO, and this is the name of the model. You can find all the names of the models they have in the website. You can load the model on, again, MPS, CUDA, CPU. Let's load it on the CPU for now. And then you can give it images, videos, or stuff like this in order for it to get bounding boxes. And then you can read the data here. So you give the frame, each frame to the model, and you get the results. And then you can plot the results and show them. Again, I use this OpenCV library to show the frames. This is just for OpenCV, not to quit. It's stupid. Yeah, let's run it on the bus image actually. I know, but this is for video. Okay, let's run it on the video directly. CPU. So a YOLO V8, again, this is the model V8, N is nano. So this is the smallest YOLO model. Let me see. YOLO V8 model taxonomy. They should have something. See if they show this. Yeah, this. So yeah, this is YOLO V8 nano. Then they have S, small one, M, medium, large, and extra large. They don't show here the number of parameters. Do they? Ah, yeah. 2.7 million, 6.4 million, 17 million, 35 million, 57 million. So they're not particularly big, even YOLO V8, which is the most recent, like one of the most recent models. It's not particularly big, that's why it's fast. But it works well. So let's see how it does on this video. So let's show the video first, actually. So this is a video from the Kitty dataset. Kitty is a very big dataset for a lot of tasks. In this case, we can use it to detect objects. This is what we want to do. The name of the video. Okay, it's not out. Okay. Let's run it from the terminal. How do you write that? LauzHack bootcamp. Okay. Go V8. Okay, let's see what happens. It's downloading the model on the go. And there you go. This runs real time. Okay. And as you can see here in the terminal, I hope you can see it on Zoom. Let me zoom it a little bit. Okay, 33.3 seconds of inference. Okay, it's very fast. Milliseconds, of course. So it's very, very fast. And it's quite accurate. It's not perfect, but it's quite accurate. You see the cards are all detected, the person is detected, and yeah, it's quite nice. I can run bigger models. So let's try to run the biggest model. So with X, we'll download the model. It's a little bit bigger, 100 megabytes. There you go. Clearly slower. You see 250 milliseconds of inference, which is 4 frames per second. So it's definitely slower. Huh? This is CPU. This is on CPU. Umbrella, bicycle, motorcycle. It's pretty good. And let's see if I run it on MPS. Okay, now 50 milliseconds of inference time. 30 now. Yeah, between 30 and 50. Quite a bit faster in MPS. And this is the biggest model. So if you need faster times, you can use smaller ones or use GPUs, of course. Okay, that's it for YOLO. Any questions? All good? Okay, then I guess we can go to the second part of the presentation, which is on image segmentation. So I don't have as much time as I thought, so I will go maybe skip some parts that are less interesting, but you can find the slides anyway. So where do we start? What's the problem setting? Okay, so what are edges and regions? A region is just some kind of homogeneous area by some definition of homogeneous. Okay, it can depend on the application, and the edges are the boundaries between these areas. That's kind of it. So with segmentation, what we want to do is that we want to separate the homogeneous areas and find a way to differentiate them. So in the homogeneous areas, they will have some statistical properties of some sort that will make them a single region. And we want to find these statistical properties. It can help with a lot of things. It helps with image compression, is written there. So these slides are from the computer vision course by my advisor, Pascal Foy. But yeah, it's cool because I'm doing an image compression project right now and I'm using segmentation to try to do it. But yeah, they help with a lot of things, and especially with autonomous driving again, it keeps coming up, but I would say most of these methods are very useful for robotics and autonomous driving. So yeah, here's an example. So on a road, for example, we want to separate the road itself from everything else. Here we have a bounding box for the vehicle, just a bounding box, not the segmentation mask. But for the rest, for the road, for example, and the lines, we have a segmentation mask. Yeah, it can be used in Photoshop as well. If you want to use the magic selection tool, can be very simple, just looking at the color difference between the pixel you selected and the rest. But it can also be like a bit more magic and try to do some better segmentation. That's what it is. The problem is a segmentation. I mean, I can skip the theory. It's just that the image, you can see the image as a union of partitions, S. And the partitions do not have any intersection between them. And some property H is true for a single partition, but is not true for their union, which means that a single partition makes sense by itself, is homogeneous, but two partitions together are not. Here, for example, this part of the road is homogeneous, but and this part is homogeneous too, but two adjacent regions are not homogeneous, hence the segmentation. So very simple ways to do this exist. So let's say we have a black and white image, we can just define some thresholds and say, okay, if pixel values are smaller than 30, they will belong to a region. Let's say the darkest pixels, like the hair or color here, can be segmented this way. Or maybe we can define more than one threshold. But it's very simple things that we can do. But of course, there's also many more complicated things. Today, I want to show a little bit of k-means and convolutional neural nets, of course. So let's start with the image histogram. What's an image histogram? Maybe you've seen it before. Have you ever seen it before, image histogram? Yeah. So on the x-axis, you have the intensity of the pixel, and on the y-axis, you have the quantity of the pixels that have that intensity. Okay. So we have a peak here with dark pixels, which are, I guess, hair and some other stuff. And maybe we have like some other peaks here. Could be the background. Maybe the background is a bit lighter, so maybe it's this. So anyway, you have this histogram. You can segment an image by looking at the histogram. For example, if you look at this, there is a very good local minimum here. And we can say, okay, whatever is less than the local minimum is one region. Whatever is higher than this, but smaller than this other local minimum, belongs to another region. And then here we have a third region. This works actually decently well. It's been used a lot. Maybe sometimes it's still used on old companies for like automated lines. I think I have an example here. Let's say you have this image and you want to it's an automatic production of, I don't know, this piece, for example, and you want to check with the camera on top of it that every piece that comes out of the machine is well made, is like correct size and whatnot. So you need to segment the piece out of the background. But in that case, you have very good lighting. Maybe like the light comes from below, so the object is very dark, so it's easy to segment it. That's why it's still usable depending on the application. So in this case, it's easy. You see there's two, like the histogram is bimodal. You have really two separate components and you can split it in the middle. If it's noisy like this, we see two separate components, but a histogram doesn't. Okay, it really is meaningless if we look at this histogram. So in these cases, it's very important to denoise. Denoise, apply Gaussian filters to like smooth out everything. Even though we lose detail, this image is clearly less detailed than this one, but this has a bimodal histogram that we can easily threshold, okay, and get the segmentation for this. We can do something a little bit more complex. Let's maybe skip these parts, but instead of doing a single histogram and a single threshold, you can separate it in multiple parts and have multiple thresholds. They are defined automatically because if the histogram is bimodal, you can just find the local minimum and use that. So then you can get something like this. We can use color as well. So in color images, RGB, for example, you have a red channel, green channel, and blue channel. What we can see here already is that, yes, the channels are a little different, but they correlate clearly a lot with each other. Okay, it's the same picture. So they all look like different black and white versions of the color picture. Okay, slightly different, but it's the same picture. So this is kind of a problem for most methods, because when features correlate a lot with each other, they're not so useful. You need to find decorrelated features. And there's a way to do this. It's the HSV space. Instead of using the three color channels, we can use these other three channels: hue, saturation, and value. Without many details, we can simply say that the saturation is, how colorful is the specific color, and it's computed this way as a maximum channel minus the minimum channel. The value is, in general, how intense the whole, the pixel is. So you get from very dark to very bright. And the hue is basically the color, okay? It remains only one channel encodes the color, the other two encodes more intensity and saturation. I'm not sure. I can come up with another word to describe it. So use the same image with the HSV encoding. So I have the value here, intensity. You have the saturation here, very different, and hue. Again, very different. And I can already see it's easier on this kind of images to do edge detection or segmentation. Clearly easier to do it on this image on the saturation channel. It looks much easier than the others. Yeah, in fact, we use the saturation channel and we can clearly see it's bimodal, so we can cut at this point and we get a nice segmentation mask. So this is just what has been done a lot in the past. Again, I'm not sure people really still use it. You can if you have these simple settings. Otherwise, it doesn't make much sense, I guess. But what people can still do is k-means. So do you know what k-means is? Okay, some yes, some no. Yeah, you don't count. So k-means is a machine learning algorithm for clustering. So you can show this. So let's say you are in a 2D setting. You have points in 2D space, and you see quite clearly with your eyes that these are divided in 4 different parts. Let's say 4 different clusters. And is there a way for an algorithm to find these clusters? And k-means is an algorithm that tries to find clusters. It's unsupervised. Okay, there is no supervision for this task. We just want an algorithm to find the different clusters. We don't know what the cluster mean. They don't have to mean something. We just want to find them. And this is kind of similar to segmentation in a way, because we don't want to know what's like a road. We just want to separate it from the rest. Then we might want to classify it as a road afterwards. That's going to be supervised. But just the segmentation part doesn't have to be. And in fact, k-means is not supervised. So here, if we want to apply k-means on an image, we can see, for example, that each pixel has 2 spatial coordinates. So we can use the spatial coordinates if we want. It doesn't make sense, but we can. I'll show later why it doesn't make sense, but we can. We can use the RGB values of each pixel. So it's going to be a 3D space with the RGB values as coordinates, and we can cluster these pixels with the RGB values. Or we can use another space like the HSV. We can use 5D space with the X, Y, and HSV coordinates if we want to. We can do pretty much whatever we want. And of course, we will get different results. And the way k-means work is that it defines a cluster as the points closest to the center of gravity of the cluster. So let's say we start with 4 clusters and we place them already in the right position. Okay, it's just a silly example. So let's take this one, mu1, as the center of the cluster. Then between all of these points, only these will belong to the 1 cluster, because the others will be closer to the other clusters. Like this point here is closer to mu3 than mu1. Okay, so it will belong to cluster 3 instead of cluster 1. So for each cluster, then the center is computed as the center of gravity of the cluster. Okay, so we take the average position of all the points because we assume that all the points have the same mass. If you want the points to have a different mass based on some other properties, you can. This is free. Yeah, mean of the points is the center of the cluster, and that's it. So what we want to do, the objective function with k-means is this one. So we take the distance between the points and the clusters, and we want to minimize this. What do I mean as the distance between the points and the clusters? So you see there's a bunch of indices here. The point is we have each point assigned to only one cluster. So all of the points here will be assigned only to cluster 1. All of the points here will be assigned only to cluster 2, and so on. So the distance we want to minimize is the distance between the points assigned to cluster 1 and the center of cluster 1, plus the distance between all of the points of cluster 3 to the center of cluster 3, plus all of the points cluster 4 to the center of cluster 4, and so on for every cluster. Okay? Does it make sense as an objective function? All right. So the way we do this, that there's no closed form solution to this. So we use an iterative procedure to minimize it. Yeah, you still have a problem. So the reason why it's difficult, like it looks easy, but it's not easy because each point can be theoretically assigned to any cluster. If you change the assignment of a point to another cluster, then the center of the clusters will move because they are the mean. But if they move, then the points will get assigned to another cluster. So it's a very difficult function to optimize. But again, there is an iterative procedure to it, and it's very popular, and it's the k-means algorithm. So what we do is that we repeat this loop until it converges. We first of all assign, so we start with random clusters, absolutely random positions for the centers. Then we assign each point to the nearest center. And then we update the center given the points, okay? So we assign the points, and then the center becomes the mean of the assigned points. And then we do it again, yeah. How many clusters? I mean, yeah, we don't. So, I mean, sometimes you may know, so you already use the correct number of clusters. Otherwise, you can run, k-means is very fast to run. So you can run k-means with multiple clusters, and then you select the number of clusters that makes the most sense, which is not the one with the lowest loss function. I didn't prepare a slide on this, but you would see, can I draw on this? Okay. I want to take out my iPad again, but you will see some kind of like elbow thing. You reduce the number of cluster and you get a much better loss. And then at some point you will stop doing this. If you still reduce the number, if you still increase the number of clusters, you keep getting a better loss, but at a slower rate. So it's better to stop. Why? Because of course, the smallest possible loss, you will get it if you have as many clusters as the points, and it makes no sense. Okay. Okay, so we can show maybe a demo. So let's say we have this point distribution and two clusters. So all of this like blue points and red points are points. Okay, blue and red just mean that in this case, they are closer to the blue cluster, closer to the red cluster. There's no classification going on. So we start with random positions for the centers. Oh, I'm adding points, didn't want to. Anyway, we start with random positions for the centers. And then if we run one iteration, what we get is, again, the two steps I mentioned. So we assign the closest points to a center, and then we move the center to the mean of those points. And if we do it again, they will move again. And at some point, you see already after 4 iterations, they stabilized. So we get these two clusters. If we look a little closer, we can see that maybe the clusters are more like 3 than 2, I would say. Maybe we can separate this one compared to the one below. So maybe we can increase the number of clusters, iterate again, and get something like this, okay? And as you might imagine, the starting positions of these centroids are very important. So if I start at a different starting place, I can get something quite different. Okay, in this case, it was the same. Yeah, and now it stopped here. Okay, terrible. This is not what I wanted. So in general, what you do, again, since it's very fast, is that you run it many times and you keep the one that has the best loss. Yeah, yeah, you initialize randomly in different ways, and then you run it many times. Okay.
It's not that.
Sorry?
In every iteration to compute something is n squared.
In every iteration, you have to compute the distances. Yes,
I mean, maybe that's a cheap operation now, but it doesn't seem.
it is. I didn't look at the how the k-means is implemented in like scikit-learn or OpenCV. They both have an implementation. They're very fast though. I'm not sure. Maybe there is a nicer like a trick to avoid all those computations. Because you don't really want to compute distances between every point and every other point in space. You want to compute distances only between points and clusters. And it's a very regular space. So there may be some trick. I don't know though. Okay, let's go back to PowerPoint. Here you see another example in which you have three clusters and they keep iterating until they stabilize. Okay. Yeah, as I said, the initial conditions are very important, but you can do this on an image. And for example, here, I think, yeah, color only. So it's just using the RGB values for the pixels. So every pixel is represented by one RGB point in an RGB space. Okay. And then you try to cluster with K clusters in this case. This is what you get. So this is the optimization process going on. And you get something like this. Okay, it's already pretty good. Especially when you have like contrasty images in which the colors are fairly different. The colors or the channels, like HSV channels. So in this case, it's very easy to segment, even with this kind of methods. Again, not supervised. I didn't tell anything to the method that is like image specific or dataset specific.
Objective here is solely the color, and you're not caring about spatial properties.
In this one, yes, I'm just caring about the color.
So the two greens are the same class.
Yes, yes.
Not class.
Cluster, yeah. Yeah, indeed. Good point. You can initialize it in different ways and you get a different result. They all kind of make sense, but some are better than others. Like, I don't know, this one makes sense just like this one, I would say. They just have a different color because the cluster is different, but it doesn't matter. It just matters that the clusters are the same. This one is not so nice because the sky is being segmented and we probably didn't want to. And if we change the values of k, of course, we get something very different. I would say k equals 3 makes sense, k equals 5 makes sense, but already k equals 8 doesn't really make much sense. K equals 15 also doesn't really make sense. Some more results, again, depending on the image, it can be fairly easy. On these ones, it's easy because they're contrasty. In other images, it's not so easy. Okay, let's show a quick demo. I should not, how do I not exit PowerPoint? Like, what do I do now? I will crash. Sorry, guys, on Zoom. Maybe I can stop sharing my screen. Let's see. And then I exit PowerPoint. And then I share my screen again. Computer science. Okay, so I have k-means over here. This is a very small notebook on k-means. So we can, I will use the CV2, so the OpenCV implementation of k-means. There's other ones, they're all equivalent. So what I do first, okay, so the image I have is this one. It's a hard image, so I do not expect k-means to do particularly well on this one, actually. Let's see what happens. So I open the image, it's the bus.jpg. I will convert it because the OpenCV representation by default is blue, green, red, but we usually use red, green, blue to plot it. Otherwise, it will be plot with a weird color scheme. So we'll just execute this and get this plot that was already there. Then what I can do is make the image an array of like size of the image and the three channels, because this is what I want to have from the OpenCV image to like a NumPy array that just has the pixel values, the RGB pixel values. And then I convert it to a floating point array because that's how k-means work. If you give it integers, it just doesn't work. Okay, and then we want to run this k-means function, which is very simple. It takes the pixel values as an input, the number of clusters k. None here is, I forgot what it is. well, we don't care apparently. Criteria, so this is a stopping criteria. You can set the maximum number of iterations. You can set a required accuracy. It will usually stop before that. It doesn't need many iterations to work. And this 10 is the number of attempts it makes before, like, so it will try with 10 different random initializations, and then we'll keep the best one. Yeah, and this is the way we initialize with random centers. Then out of this function, we will get the compactness score. So it's the loss function. We will get the labels and the centers. Okay. So maybe just to see what happens, let's print the labels. I will now run. So these are the labels. The labels are going to be as many as the pixels. So each pixel will have a label. Okay. In this case, it says that the first pixel of the image has label 2. So it belongs to cluster 2. Second pixel belongs to cluster 2. Third pixel belongs to cluster 1, and so on. The centers instead are these. So I said 7 clusters. So I have 7 centers. And each of these coordinates are the coordinates in the whatever space I'm using. In this case, I'm using the RGB space. So these are actually RGB colors. So what I can do to show the clusters is that I take, so this segmented data, I want this one to be the same shape of my image, but instead of having the color for each pixel, I want to have the color of the center for that pixel, okay? So I query the centers with the labels, and I get it. I get just what I need. I will reshape it to the size of the image, otherwise it's just a flat array. And then I can print it. So this is the result for 7 clusters. So you see that it's segmented very well, the blue of the bus. Maybe I can open the original image again. So we have here the blue of the bus, this building, which is mostly yellow, the road, which is mostly gray, and yeah, maybe the stop, the no parking sign here. Yeah, so what I see from here is that this part of the bus, again, has been segmented very nicely. The road, I would say, is mostly the same color, but the shadows, of course, are in the way. They've been segmented separately from the rest of the road. Also, the building here is not really great. But yeah, that's k-means for this image. It's probably too hard for k-means. We can do the same with pixel locations. So what I'm doing here is exactly the same thing, but I want to give to k-means the pixel locations instead of the RGB colors. Okay, just the locations, the XY locations. So the first pixel top left of the image will be 0, 0. Second pixel will be 0, 1, and so on. It makes no sense. It makes no sense. I'll show you why. So I give 10 clusters, execute. So this is what I get. It absolutely makes no sense because I am clustering a regular grid of points. So of course I get this kind of Voronoi diagram. It makes absolutely no sense. I just wanted to show what happens if you do that. But what we can do is that we can concatenate the pixel values and the pixel locations. Okay, if we want to use both. And we can run k-means again. Maybe that's right with 7 clusters. Yeah. We get something like this. Maybe 7 clusters was too little, but I can see, from this image, I can kind of see one thing. So one thing is cool. It's segmented this is probably the bus. So yeah, kind of correct. But I really see, a line here, which is really dependent on the coordinates too much. So what we can do, maybe we can print here. We can print the mean of the pixel values and the mean of the pixel locations. Here, you see the pixel values have a mean of 117 and the pixel locations of 472. So they're just scaled differently, the pixel coordinates are going to have more impact than the pixel values. So we can maybe scale them down. Let's say 5. Let's say 3. What happens? Let's see. Okay, something like this. Clearly less impactful. Okay. You can play these parameters a lot. You will get very different results. And of course, the number of clusters changes everything a lot. Let's see what happens with like 4 clusters. I'm curious. Oh, I mean, the building got better, but then the bus got integrated with the building. I would say definitely this image is too difficult for k-means, but you can try it out if you need segmentation in your tasks to see how it works, because it's very fast and it's always worth it to give it a shot. Sometimes it can also be used in conjunction with other methods. If you get a feature map, then you can use k-means to do stuff with it. Like I said, with half transform. Sometimes you can use these classical methods on neural networks as well. Yeah.
So we are not saving anything, right? Like
No.
in terms of ways, so
No.
if that every time compute again and again for the same folder, no. Okay.
No. It's a direct segmentation of this image only.
And in the long run, then is it computationally efficient when you're working with KNN?
Let's answer your question by running time. Import time. Start equals time.time. And equals time.time. Wait. And minus start. So it's 2.9 seconds to run it 10 times on this image with 7 cluster. What is it? I think it's not bad, but it really depends on the task. YOLO is clearly faster and in a sense more efficient. But it changes a lot. If you run it only once, of course, it's 10 times faster. If you use less clusters, is almost directly proportional to the number of clusters you use. Not sure it answers your question. No worries. Okay, that's it for k-means. All good. Let's go back to PowerPoint. Okay, can we do something better? Yes, we can use CNNs, the ubiquitous CNNs. There's only one problem. So CNNs, like you saw that if we run convolution, the output feature is a bit smaller than the input feature. If we use padding, then the output feature is going to be the same size of the input feature. They do not increase in size. So for producing segmentation masks, if we want to use convolution, so let's say we go like we apply convolutions to the image, we go down in size, down. At some point, we need to get the mask back, and the mask has the size of the image. So we kind of need to do the opposite of convolution and go up in size. Okay. So we need something to do this, and I don't know if you saw it. It's probably here. Yeah. I don't know if you saw it in the first week, maybe. Transpose convolutions, which is similar to a convolution. It's implemented in the same way. But what you do is that you pad the values of the input layer with other values. Can be zeros, can be other stuff, can be linear interpolations. So this like light blue pixels are the input pixels for this layer, input features for this layer. And then you increase the size of the input by adding all this other padding in between. And then you use your convolutional filter to get the output. Okay. So if you look at the size of the input, this is a 3x3 input because there are 3x3 light blue pixels, and the output is 5x5. So effectively increase the size. And you can do it many times, just like with the convolutional block, normal convolutional block, you do it many times and you get to very small sizes. You can do this many times and get to very big sizes. It's the same thing. So this is where the concept of UNet comes from. May have heard of this model. So with the UNet, you apply many convolutions and you go down to this like single big representation vector for the image. And then you want to generate, so you can see the first part as an encoder that encodes the information of the image down to the latent representation. And then you want to go back to the size of the image and decode this latent code into a mask that you can use for segmentation. So this is idea in UNet. Okay, so the part on the left is convolutions. The part on the right are transpose convolutions, which is what I just presented. So UNet works nicely. Again, you need to train it. It can be a very big model. It's still used. But again, it needs quite some data to train. I'm not sure it's super fast. Actually, didn't check, but I don't think it's particularly fast. It depends on the size of the model, of course. But you get good results. It's surely better for complex data than k-means. Very surely better. Then there's like, once you have this kind of approach, you can also see UNet as a general approach. You know, you go down in size and then you go back up in size. You can do many things with this. This is a line of research that is quite popular. I don't know. I see it and then it disappears for a while and then I see it again and then it disappears for a while. I think it's resurfacing nowadays, which is some kind of recursive segmentation. So you start mosquitoes. You start with the image, you give it as an input to your UNet, let's say, and you get a mask, but then you give the mask back as an input to the UNet in conjunction with the original image, and then you get a refined mask, okay? So you can train the model this way, so you have a recurrent model, and you can train it in a recurrent way so that the mask gets better over time, so you supervise every recursion of the model. And then when you use it, it actually gets better over time. This has been proved. If you train it right, it gets better over time.
The round after the first one, and you're giving the input is so that the inputs here are 3-dimensional, and then the input later is 4-dimensional, something like this.
Yeah, it's more like, let's say the input here is, I don't know, 1024 times 1024 dimensional, because there's a full image as an input to the network. Let's say the size of the image is 124 times 124. And the input here is instead 1024 times 1024 times 2, because you have two images as input. One is the original image, one is the segmentation mask.
Okay, I thought that the mask looks like it's binary, so I was thinking it's 3.
It's binary, but it's still 1024 times 1000. It's still an image.
Sorry, I meant channels.
Oh yeah, the channel is 1. Yeah. You add a channel to the image, basically. Yes. So you start from a 3-channel image and you get a 4-channel image that you will use an input.
And then you can do that indefinitely.
Yeah. Usually, I mean, I've seen people doing it up to like 5 times or so, even 8 times, I think. So probably it gets a little bit worse if you keep doing that. I'm not sure, but if you do it a few times, it does get better. And then, of course, there's vision transformers. So you can do a very similar thing with vision transformers. And what you need to do after, so you can, instead of processing the image with a CNN, you can process it with a vision transformer and basically substitute the CNN layers with some transformers. And what you want to do in the end is that you want to get the output of the transformer and upscale it, because this you still have to do. So you have to upscale it so that from the latent representation, it becomes image representation, and you can get the segmentation mask. So what it does in this case is that you have like 3 queries to the transformer, one for a tree segmentation, one for sidewalk, one for person. And then you multiply these by the embeddings that you get from all of the image patches and Computer's Cloud product. You get all of this, and then you need to upsample all of these like low dimensional masks into the high dimensional final segmentation map. It's a very similar approach to the UNet. So you go down in size with the transformer, and then you go up with some upsampling steps, which can be transposed convolutions again.
And
I think, yeah.
concretely, those queries mean, I mean, what does a query there look like?
Which query, sorry?
We said the tree
This?
sidewalk person, so they're
An embedding of the word tree, for example.
oh, words.
Could be.
Okay.
Literally. Oftentimes, these kind of models can be trained jointly.
Okay.
With like a model that already encodes queries nicely. They don't have to be. I think this works already without any other pre-trained text part. You can just give it, probably has like a predefined number of classes, so of tokens that you can give to query. But then, yeah, then you just give the token.
So they're not image patches or something?
No.
I don't remember what you showed at the beginning of the card with templates.
Uh,
It was really, really early on in this thing. So you could do segmentation with templates, but it's not useful.
oh, yeah. No.
So it's not
No.
these queries of
No.
text.
No. They're not. This is text, yeah. Yeah, this is just another example in which you do a similar thing. So you go down with the CNN and then you use a transformer after going down with the CNN. And after the transformer, you go up again with the transpose convolution. Very similar thing. There's many, of course, approaches that are similar to this. But yeah, that's kind of the idea. Okay, before I go to the segment anything model, stop share, exit presentation, share again. Let's go to YOLO for a second again, because there's a cool thing that you might have noticed here, which is this model. So YOLO V8X, so this is again the largest model. You can use a smaller one if you want. Segmentation, okay. Yeah.
People like come up with CNN. Is it that they're just like testing it out, like they try out things, or is it there's like some theory behind it, like they think, oh, it could work better because of this.
I would say in practice, it's mostly just testing it out. There is some theory behind it, but in practice, it's a lot of testing it out. You can, like, we know, for example, that transformers work very well on many things, and there's also theory behind it. So when we want to do some kind of task, we can say, oh, let's apply a transformer. Then maybe we apply it and it's terrible. I guess you have an experience like this in the Intro to ML course, where we had the guy behind you, because we also we had a task that you could do with MOPs, CNNs, and transformers. The transformer model was the worst, because if you don't have enough data and enough compute, it's not really good. It isn't really. So it's a lot of trial and error on this kind of things. Really a lot. It's very dataset specific, very task specific. Like even transformers themselves, there's a reason why they came out now, because now we have enough compute to use them. Maybe somebody tried them before and it just didn't work. Oh, yeah. So it's actually like a philosophical question. Does the let's say model innovation come first, or does the hardware innovation come first to enable the model to work? Like, did CNNs got developed because of GPUs, or was it the other way around? Of course, probably both, but that kind of raises the question. Maybe the machine learning research should start again from FPGAs and implement super fast things so that we can use some crazy architectures in hardware instead of in software and have them go very fast to try them out. This is an open question. Okay, so let's get back to YOLO. So this is YOLO V8 extra large model segmentation. So this will do both object detection and segmentation in a kind of fast way. Of course, it's a little slower than the other one, but not that much, if I recall correctly. Oh, did it crash too? Yes, it crashed. Nice. Downloads, LauzHack, code. Okay, let's see what we get. All right. So now you see that for the classes that YOLO produces, you don't just get the bounding box, you get the whole segmentation mask, which can be useful for your task. I mean, I guess it depends what you do. But you get a much more precise location. A bounding box is a kind of a general idea of where the object is. It's in this box, but it's a rectangular box. The objects are not rectangular. They can be like tilted, can be rotated. The segmentation mask gives you like pixel by pixel where the object is, and you can do this with YOLO as well. It's pretty fast. Yeah.
When should we use segmentation tasks to do object detection, and then we do raw object detection standard YOLO?
You mean like for what tasks?
I mean, we want to define the boundaries. We have two options.
Yeah.
Use YOLO as is.
Yeah.
Or use some segmentation task and then say that we have segmentation mask for this class and use segmentation mask to define the boundaries for the box.
Yeah.
So when
it's for the boundaries. I see.
So when the option with segmentation is better than the option with the object detection.
So in the case of YOLO, I believe that the box is anyway not computed from the segmentation mask. They are like two branch. The network is the same at first, but then it divides in two branches. One that does the outputs the box, and the other that is upsampled through the transpose convolutions and gets the segmentation mask. So I think that if you do the segmentation, you need to run the first part anyway. So you get the bounding box from the first part anyway, and the segmentation mask cannot go out of the bounding box. So it's not that you compute the bounding box from the segmentation mask.
Maybe we can not use YOLO, but use net. We have segmentation for the whole frame.
Yeah.
With several classes.
Yeah.
For each class, we can say this is the most the top pixel. This is the bottom pixel. The most left pixel. The most right pixel. And this is our one.
No, sure. I would say simply that. I would simply say that probably the object detection without segmentation is an easier task. So if you don't need the precise location, you can go for the easier task. Yeah.
Easier to solve.
Yeah. There's an even more difficult task, I believe, which is to predict the 3D bounding boxes of these objects. So these are 2D. But in autonomous driving, for example, I would want to know that a car that is in front of me has a specific direction. I want to know if it's going away from me, if it's going sideways, where is it going? So I don't just want a bounding box. I want to know what's the direction of the car. So it's a completely different problem with the fairly different solutions. And it's very active in research. It's not solved at all. It's that's actually one of the things the Kitty dataset is for, to compute these kind of things. Maybe I can give you just a pointer if you're interested, because I don't have it in the slides. Yeah, so what this model does, you can, it's a terrible image, but you can kind of see it. So this is a 3D bounding box. Don't know if you can see it. This is the 3D bounding box of the car, and it's oriented. You see there is the orientation. So this is what you want to get from the image. And it's very hard to do, actually, especially if the only thing you have is a single stream of images. It's like from one camera. It's way easier, it's still hard, but way easier if you have two cameras, stereo configuration, and it's probably even easier if you have a LiDAR. So if you can use all of that, so stereo and plus LiDAR information, so depth scan. But yeah, it's an active research task. It's very cool. They close. Okay, time. All right, so the last thing I want to do today, it's a fairly quick thing, so it's all right, I guess, is the segment anything model. So it's a segmentation model proposed by Meta in 2023. So it's one of the latest models, if not the latest. It's a big model. They define it as a foundation model for segmentation. It's very interesting because of a few reasons. So I'll try to go through the reasons more than the architecture. But let's look at the architecture first. So you give an image as an input, and then you have an image encoder. The image is this size, again, fixed size. The image encoder is a pre-trained visual vision transformer, and it's a masked autoencoder. So they pre-trained a vision transformer masked autoencoder on some data set. Then they keep only the encoder part, and they use it to encode the image in some kind of latent representation. Okay, this is a start. This is what they get. Then they have this masked decoder, which again, I mean, takes this, does some like transpose convolutions, upsampling, whatnot, and you get 3 masks. They decide to output 3 every time because, let's say in the case of scissors here, you may want to have the full scissors or maybe just one part or another part. So they kind of output 3 masks that you may be interested in. And the cool thing is that you can prompt it. So you can prompt it with text. They use clip as a text encoder. We will see clip next time, but it's just a way to encode text that is related to images. So they use embeddings from clip. So I give it the text, let's say the text is scissors, and clip encodes the text in some latent representation, which is given to the mask decoder with the image embedding, and the mask decoder will output some mask that is related to the image and to the text that I said. And you can query this not just with text, but you can give it a bounding box and say, can you like segment what is in this bounding box? Or with points. So you click something on the image and you're like, I want to segment this object, and we'll kind of outline the whole object. You can also give it a mask, but not particularly important. And the mask decoder is attention-based, so it's a bunch of cross-attention between the prompt encoder and the image embedding, and vice versa. They do both ways. And then they upscale. Yeah. Oh, yeah, it's written there. So they give you a segmentation mask and an IOU, predicted confidence IOU. The cool thing about the model, I will show you in a second, like how the model performs, and it's quite amazing actually. But I think the coolest thing about the model is that you can use it to train itself and to train other models. So the way they trained it is that they had like a big data set with 11 million images from the internet or from some other sources. And they, of course, didn't have the horsepower to segment everything themselves, annotate everything manually, and give it to the model to train. So what they did is this kind of cycle in which they would label some images and then ask the network to annotate, so to label itself the same images, compare, so train on those. This is fully supervised. But then they would ask the network to label other images, to segment other images, and get these data given to the annotation experts. Yeah, the door is hard to close. They would give this data to annotation experts. They would check it and would just modify it if needed. Okay, sometimes it would be good, sometimes it would not be. So they would modify it and keep going. And the more you loop in this cycle, the better the model gets and the less need you have for human annotators. And they end up with this big data set. So they end up with 2 things. 1, a very good model, and 2, a very good data set. So they end up with both at the same time. And the data set is available as well, more than 1 billion masks. And the model is available too. And this is a typical result from the model. So you can see it's quite good if you look at the annotations. This is really great. Like even like separates all of these things. Was that vegetables or so? Looks like candy when it's segmented, but it's not. This stuff as well. So it really able to like see this kind of homogeneity that we perceive as humans in the regions of the image. This is very cool to see. It doesn't output classes though, okay? It's not trained to output classes. It only knows they're different. It doesn't know the class, okay? You can query it with a prompt, yes, but it doesn't really output a class by itself. The cool thing is that it can be used for many other things. So one thing is this. So you want to have edges. So you can get the segmentation masks and then apply a Sobel filter, just like we saw at the beginning of the talk this morning, and get the edges. And again, the Sobel filter is still used. Nice. This is from their paper in 2023.
Can you explain that one again? What's the process that you use a servo filter and then give that to Sam?
No, you take, sorry, you take the image, you give it to Sam, you get the segmentation mask from Sam, and then you apply a Sobel filter to the segmentation mask. The segmentation mask, by definition, will have like steep difference between regions. So it's very easy to find edges with just classical methods like a Sobel filter and non-maximum suppression.
Oh, I see, but then it's put in more detail than the ground truth example.
Yeah, so one thing is in these kind of tasks, ground truth doesn't mean anything. It's more, they also say it in the paper, they evaluate on some ground truth on this kind of tasks, but then they're like, yeah, then we looked at the ground truth and we didn't agree. So let's give this outputs to like humans and just ask them to rate the quality. And they show, oh, we're the best, blah, blah, blah. Yeah, that's not, otherwise they wouldn't write the paper.
It's the same. Like 4 or 5 different colors.
Here?
Yeah.
Here's depend on what you ask. Maybe you want to ask like wings and body. I guess this is just to show the capability. I think this is from, so the dataset has been segmented using SEM. These images are from the dataset. So this is the kind of masks that you can get from the dataset if you want to choose the dataset. But if you want to get the full plane, you can get the full plane, for sure. There's another cool task that it's called zero shot text to mask. So again, you ask for a wheel. The SEM has not been trained to do this. So you ask for a wheel and it gives you a wheel. Or you ask, in this case, you ask for a wiper, but you don't get it. It makes a mistake. But you can ask for a wiper and click the pixel, and then you get the full wiper out of the pixel. Here's wipers. You still click one pixel and you get both wipers. This is really amazing. Okay. Let me. Right. It downloads the model. It's a bit bigger, like 350 megabytes, but it still can run on CPU. Okay, so I'll run it on CPU. I tried running it on MPS. That didn't really work. Not sure if it's on like my side or their side. So I'll run it on CPU. Will take a couple of minutes to segment one image, which is too slow if you want to use an autonomous car. Yes, but the point is, it's still usable on a laptop if you need to. It's not so slow. Way slower than YOLO, but it's usable. But while it computes, I think one of the coolest thing about SAM is that you can use it to create a data set to train another model. Okay, it's kind of a distillation process. So let's say you need to segment fast something, but you don't have like, and you have a data set, but it's not annotated. I guess like your case, you can use SAM to annotate the data set. So you use SAM with some queries. So you can use it automatically, sure, but you probably wouldn't get exactly what you want. So you can use SAM in conjunction with some human that is in the loop for this annotation. So you get the annotation from SAM, and then you can refine it and say, oh no, I was actually looking for this, and click that point or stuff like that. And then fairly quickly create a data set that you can use to train a faster model on, like YOLO. So this is something that is very cool. I think one of the coolest thing in SAM is that you can do this.
But it's totally general purpose.
Yeah.
But what I said 11 million images is quite a lot, but what's in it's human, they're all color photos, I guess.
Is it whole?
So they're all color photos. The data set that they have.
Yeah, sorry.
Trained SAM,
Yeah.
color photos, for example.
Sorry, I don't understand the word. I'm very sorry.
Photographs that are
Uh-huh.
RGB,
Oh, okay.
different colors.
Yeah, I think so. I think so.
And so for you do medical images that have what kind of channels? So
And different,
they're not usually light.
like very, oh yeah, sometimes it's just gray levels, sometimes it's
Okay.
very different fluorescent levels, so like multiple channels.
Yeah. So something like those. I mean, is it like the features matter? The features that it gets are basically edges and 3D biological shapes, so they exist in normal photos.
That's a
Or-
good question. I think the only answer is to try it.
Yeah.
Do try it. Let me know how it goes.
Maybe you can tune it. Your data.
I mean, yeah, the weights are available, so you can fine tune it for sure. I don't know if people have done it. So here's what I get from the bus. It's probably too much for what I want, but then again, I can say, oh no, I only wanted this, I only wanted that, and so on. So you get all of this. So you get the class. Let's say like here, you have class 5 with confidence score 0.98. Class 5 doesn't mean anything. It doesn't give you a class for that. It just tells you that it's one class, whatever that is. So it recognizes like the windows, the like balconies here, the roof of the bus in general. Is there like this blue? Oh no, this blue one is the floor, and you have the 2 people and some other things. Okay, it's really too much in this case, but it's really cool. And how long did it take? Yeah, like 2 minutes and a half. It's not too bad. One cool thing that is not useful in, say, autonomous driving, but it could be useful in other scenarios, is that you can query the model, but you don't have to pass the image through the encoder again. So you can pass the image to the encoder once. The encoder is slow. The query and the decoder are very fast. I think it's written there. No, it's not. But the query and the decoder are very fast. They can run in like a second or half a second or so. So you can give one image to the encoder, encode it in like 2 minutes, and then query it multiple times if you want. Yeah.
Are the classes the same? You take another picture. Like, for example, class 21 is a window, or class 61 is a window.
No,
you take another...
no, they're not the same. No. No, because the model has no idea what it's doing. But the fact that you can query it with point locations and words, I think probably solves that. Let's go on the internet, segment anything. Demo. Yeah, they have it. So you can do this online. It was not this one. This one. Demo. I have read everything, yes. Okay, well, let's click something. This one. You can upload your own images. So maybe you can try it. Like you don't have to download the model and the code. You can just use the website and check what Sam can do. So I can, you see, like when I hover the mouse, I guess segmented the dog immediately. The segmentation is very good. Ground. This is excluded for some reason. The tree, it's so blurred, it's barely recognizable. So in general, it works very well. I wouldn't be too surprised if you can generalize to some very different things, but you never know. And you can also query it with bounding boxes. So I can say, I want the object that is inside the box. It's the dog. It doesn't let me query text on this demo. Probably you have to do it locally. But in this demo, the inference, so the image encoding is on their backend, but the rest is CPU on the browser. It's actually run on my computer, the second part. So the second part is fairly fast. It's not too slow. It's a bit sluggish, yes, but it runs. It's the first part that is slow. Cutouts. This I don't know what it is. But yeah, I think that's kind of it on my side. I hope you had a lot of fun and you didn't fall asleep and you learned something, I don't know. Well, feel free to ask any questions.
Questions? Thank you.